So vertical asymptotes and holes. How do we tell the difference? Well, it's nice to say what we said in the PowerPoint, just, hey, if you can factor the top and bottom, it simplifies out or not, but let's actually take a look at it. So let's consider the function f of x equals x minus 2 over x squared minus 2x. This is the same function that whose graph is on slide number 5 of the PowerPoint. So we've already seen the graph, and you could actually even pull it up and look at it whenever you want there. So the idea is, first of all, that we have to start by finding the domain, because the whole idea is that there is this vertical line that the graph kind of has to approach but not touch as it, as we get close to that x value. Or a hole, which is literally just like somebody reached in and plucked a point right out of the graph. So in both cases, we're looking at something that where the function doesn't exist. So we start with the domain. And the domain comes from the denominator knowing which values make it 0, and then excluding them from the domain. Again, the numerator and the denominator are both polynomials, so all of the operations in the numerator can always be done. All of the operations in the denominator can always be done. It's only this division we have to worry about, and only if the thing we're dividing by comes out to be 0. Simple enough to do. A quick bit of factoring. And from this factor, x cannot be 0. And from this factor, we get x is 2. These are the two values that have to be excluded from the domain. So the domain is negative infinity to 0, skipping over 0, but then continuing on to 2, and then skipping over the 2, but then continuing on forever. So as we can see, there are gaps in the domain at these two locations. So the question now becomes, how do we know which one is a vertical asymptote and which one is a hole? Or perhaps they're both vertical asymptotes or both holes. There's no rhyme or reason to it. Every function is different, so we can't assume that just because we know what's going on with one of them that we automatically know what's going on with the other. So the kind of nice thing is that we've already factored the denominator here, and the numerator actually also is already in factored form, although it might help to actually wrap it up in a set of parentheses. The idea here is that the x minus 2 is a common factor in both the numerator and denominator, so it can be simplified out. Of course, when you do that, you're actually fundamentally changing the function in one very specific location. Now, this is actually not true. This equals 1 over x. And we're going to explore that in a moment. But what I did in the PowerPoint, and what I'm going to do here, is I'm going to write something next to this. 1 over x, but x is not allowed to be 2. We already know that x is not allowed to be 2 in the original function, but there's nothing in this function to prevent that. When we simplified this factor of x minus 2 out, when we removed it from the denominator, we also, kind of accidentally removed this, because this gap in the domain came from the factor of x minus 2. If we remove the factor, we kind of accidentally remove the gap. So just 1 over x by itself has no problem whatsoever with x equals 2. But the original function did, and we have to preserve that if we truly want them to remain equal. That's actually part and parcel of how we know that one is a hole and one is not. That there will be a hole at one of these points and that the other will be an asymptote. So now's where we have to actually look at what's going on with the function around those places. So, now when I say around x equals 0, I mean in a very, very highly localized set of x values, an interval around to both sides of x equals 0. That is to say, I can't actually use x equals 0, but I can use x values on either side of it, and they can be as unimaginably close to 0, well, as you could possibly imagine, and even then more so. So for example, if we're looking at, on the x-axis, if we're looking at 0 as a place I'm not allowed to be, I can be at -1 or +1. Those are the two closest numbers we would think of to 0 because we usually think in terms of integers. However, there is a whole lot of space in between -1 and 0 and between 0 and 1. Like for example, I could go to -0.1 or +0.1. And even then, as tight as those seem, it's all a matter of scale. We could actually expand this out and suddenly there's a lot more room to play with in there. We could go even closer. We could go to -0.01 and +0.01. We can keep on doing this and get as close as you can possibly imagine to 0, just as long as we never actually reach it. So what I'm going to do is exactly that and look at a table of values. So what I'm going to do is build a table of values for the function. I'm going to use -1, and then over here I will use +1. Just like I did on the number lines. And I'll evaluate the function each of those x values. But then I'm going to scooch in closer. Again, as we just saw on the number lines. So now I'm getting closer to 0 on both sides, but not actually reaching it. And then, closer still. And as I indicated with the number lines, we can continue this process as much as necessary. Let's take a look at this and we'll decide whether we need to go much further. So, around x equals 0, now remember, we're using this function. This is the original form of the function, and that's what we need to look at here. So, when x is -1, well, at this point we should all be able to evaluate a function, so I'm gonna take the liberty and fill these in here. When x is -1, the function is also -1. When x is -0.1, again, using a calculator, we should get -10. And when x is -0.01, we should get -100. What we see here is that as the x value gets closer to 0 and then even closer to 0, the y values are actually getting larger and larger, negative, but larger in magnitude. If we were to continue this and go 0.001 negative, the output value of the function would be -1000. So the closer we scooch in to 0, the bigger in magnitude this output value is going to be. Repeating this for the positive side, when x is 1, the output is 1. When x is 0.1, the output is 10. when x is 0.01, the output is 100. And again, if we were to continue this and go to 0.001, the output value would be 1,000. So we see the same kind of behavior where the closer we get this guy into 0, the bigger this is getting. And that fits the definition of an asymptote, that as x approaches 0, f of x approaches either positive or negative infinity. And that is the very definition of an asymptote. Now, the reason that there's a hole at x equals 2, as opposed to an asymptote, is going to be based on similar reasoning. Now, we're going to have to build a new set of tables here, with a new set of x values and a new set of y values. Now, before we do that, let's take a look again at the number line concept, with 2 being in the center as our target, and the closest integer values to 2 are 1 and 3. Now, what we did before, when we were centered on 0, it was kind of easy because of the symmetry around 0. It was basically the same number to positive and negative. In this case, we need to be a little bit more careful. The idea was that we started out at a whole number to either side, but then we scooched it in, we're only 1/10 to either side. Well, 1/10 to either side of 2 is actually 1.9 and 2.1. So 2 minus 0.1, 2 plus 0.1. We can, as before, kind of blow that up. And we have 1.9. In the middle, we still have 2. And on the right side, we now have 2.1. So again, we take this seemingly tiny little spot and blow it up into something bigger, and we have a lot more space to work with there. What we would now do is, like with 0, again, it was easy then because of the symmetry, but really what we need to look at is the distance. After going 1/10 to either side, we then want 1/100th to either side. So if we do 2 minus 1/100th and 2 plus 1/100th, we get 2.01 on the right and 1.99 on the left. So we're going the same distance to either side, starting at a whole number to either side, and then 1/10, and then 1/100th, and if need be, we'll go to 1/1000th. So we can now start populating our tables. So again, we're going to have a table with the x value and the output value as we approach 2 on the left side, and again over here as we come at it from the right side. So we start one whole number smaller and one whole number bigger. We then have 1/10 smaller and 1/10 bigger. 1/100th smaller and 1/100th bigger, and so on. Now, again, we use a calculator here. We already did this before from the previous table, so we can kind of get away with using that. But here we get kind of a wacky decimal, which is not to be, not surprising really. I mean, it's It's not a very nice input value, and it's not a very nice function either. 0.5263, etc. Yeesh. But while we've only taken one step, we can already see this didn't get bigger like before. It actually got smaller. Now, whether or not it got bigger or smaller is actually not as important as does it look like it's going to end up going towards either positive or negative infinity? And that's hard to determine just looking at two things here. So let's go a step further. On the next one, it goes to 0.5025, and again, using a calculator, totally acceptable. That's why we have them. So, again, it shrunk, but only by about 2/100ths this time. I'd say this is pretty convincing that it's not going to negative infinity or positive infinity. It would have to blow up tremendously, and it definitely is not doing that. But let's just go one more step to make sure. 1/1000th. So again, we're scooching up really close to x equals 2, but we're not actually getting there. And now we get 0.5002, etc. Okay, so we're definitely not blowing up infinite in either direction, either positive or negative. Let's check the other side of 2. So this is what's happening as we come at it from the left. Let's see what's going on as we come at it from the right. So here we get 0.3333, etc. Again, using a calculator to fill all these in. Nothing wrong with that at all. When we go a little closer to 2, we go to 0.4761, etc. So we did get bigger, but not really all that much. We're still looking at a pretty small number. Let's go closer. 0.4975, ... Again, we did get a little teeny bit bigger, but not enough to really convince me that we're going anywhere fast. In fact, actually, it kind of almost looks like these guys are both kind of coming together at about 0.5, although we don't actually know that for sure. So let's just go one step further, and we get 0.4997, etc. So again, what we see here is that this is not approaching infinity. We don't have that same thing that we had when x approached 0, where f of x went to either positive or negative infinity. We seem to be sticking with entirely finite numbers, and there's no indication that these are ever going to go beyond where they are now, really. There's nothing to say that this is going to suddenly, out of nowhere, just balloon up to positive infinity or negative infinity, and the same thing over here. In fact, everything seems to be very nicely concentrated there. Now, the difference here, again, the way we can tell without having to go through this table business is by looking at the factors that caused those gaps in the domain and seeing, did it cancel out or did it remain? Now, part of the reason why this happens is that this simplified function is mimicking everything that function does. In fact, aside from this statement, they are equal. I mean, this is what truly makes them equal, but as long as we stay away from x equals 2, these two things are actually identical. Well, did we ever actually use x equals 2? No, we got as close as you can imagine. We kind of cheated the system there. We kind of snuck in and got just as close as you can imagine without actually touching it. So as far as these tables are concerned, these two things are actually equal because we never actually used that. And that's the only exception that is necessary to make these two equal. But since we didn't observe it, we've got this much simpler form. And to be honest, there's nothing wrong with x equals 2 here. As we said, there's absolutely nothing wrong with x equals 2 in this. So this graph would have a point there. And that's kind of what I'm getting at. The graph of this function, x minus 2 over x squared minus 2x, and the graph of 1 over x are virtually identical graphs. The only difference is that we have to pluck that point right out of it. So let me draw that. So 1 over x is the basic rational function. So from having seen that earlier in the semester, and from rehashing it at the beginning of this lesson, we know that this function goes like this. Now, this is y equals 1 over x. This function, however, well, remember that I said it should be exactly the same except for that. So I'm going to start by drawing exactly the same graph. It's going to have the same vertical asymptote, the same horizontal asymptote, and it's going to have the same, almost the same shape to its graph, except that the graph of f of x equals x minus 2 over x squared minus 2x has to be missing this point right here. They are identical graphs. The only difference is, for this one, that one single point, we reached in and plucked it out. Because this guy is the same as 1 over x, except it has this additional rule. 1 over x doesn't have that rule. There's nothing wrong with x equals 2 here. But there is something wrong with it here, not because of what you see in the fraction 1 over x, but because of what you saw in the original function. This factor of x minus 2 caused x equals 2 to be a problem, to be something that had to be excluded from the domain. So that's what makes it a whole versus an asymptote. Because aside from that point, and we would have no other way of knowing that that point is a problem except for the factor that caused it, which then simplified out. And aside from that point, this simplified version and the original are identical, aside from that one single point. So when you have a factor that simplifies out of the denominator with a matching factor in the numerator, that's where you're going to have a whole, because that's where you're going to have this simplification and this two equivalent forms of the same rational function differing only by 1 point. Values that, or factors rather, that remain in the denominator after simplifying, well, whatever it did in the original is what it's going to do again. and that is typically an asymptote. So holes are kind of the exception. They only happen like this. You can pretty much assume if there's a gap in the domain, it's probably an asymptote, unless there is a simplified version, aside from a point, or maybe two, depending on how many factors there are that simplify. So that's the deal. Factor remains asymptote. The factor simplifies out, whole. And that's the explanation for it, but honestly, you can kind of just go with the rule. All right, more on horizontal asymptotes coming up.